Welcome back, everybody. This is going to be part 1 of 3 in my lecture series on how to find zeros of higher degree polynomials. Let's get started. A very powerful tool that we have is called the rational zero theorem, and this gives us a short list of values to sort of guess and check here. If f is some nth degree polynomial, remember all that it means is that I've got a naught or some number plus something times x plus something times x squared, so on and so forth, up to something times x to the n. With integer coefficients, that's what this symbol means, right? Integers. If you remember that from way back in the beginning of the class. So if it has integer coefficients, this tool helps us out. It tells us that rational roots of the polynomial have the form where the numerator is a factor of the constant term and the denominator is a factor of the leading coefficient. Let's see how that helps us to solve problems like this one. Fully factor this polynomial. Well, here are my list of potential roots. Notice that all of my coefficients are integers. So I know that all of the roots have to come from this list. They are numbers that look like factors of constant term 6 over factors of leading coefficient 2. Let's write out what that list looks like. My factors of 6 are 1 and 6, 2 and 3. But I could also have the negative versions of all of those. Over factors of 2 are 1 and 2. So if I wanted to write out the full list of potential factors, for this one there's quite a few, it would be, I could have plus or minus 1, 1/2, 2, 2 over 2 would give me 1 again, 3 over 1 is 3, 3/2, 6, and then 6 over 2 would give me 3 again. So these are the list of roots I have to check. So what do I do with this information? You'll notice grouping isn't going to help me fully factor this guy. But I know that one of these gives me a factor. Remember, if 1 is a root, for example, then x minus 1 is a factor of this guy. So how do I discover what they are? I've got to guess and check from this list a little bit. And you may start to see some patterns as you get more practice with this, but practice makes perfect. So let's suppose I have absolutely no intuition about what it might be, and I go to pick 2. Let's try 2. Just because I see a 2 here, I'm not sure. Okay, so I've got a 2 here. Now I can use my synthetic division to quickly check whether this divides evenly. Remember, for it to divide evenly, that means I should be seeing a remainder of 0. So I'll get 2 minus 3 minus 11, 6, and I'll bring the 2 down. 2 times 2 is 4, add down to get 1. 2 times 1 is 2, add down to get minus 9. 2 times negative 9 is negative 18. Add down to get negative 12. Uh-oh, that one is not a factor because I didn't get a remainder of 0. Why don't you pause the video here to see if you can guess and check some other numbers until you hit the right one. All right, I found the factor. It ended up being 3. That 3 is a factor of 2x cubed minus 3x squared minus 11x plus 6. So what does that mean for us? That means we can write 2x cubed minus 3x squared minus 11x plus 6 as x minus 3 times the quotient, 2x squared plus 3x minus 2. Oh, and my head is in the way. There we go. Why don't you pause the video here to see if you can finish fully factoring? Here is the fully factored version. I get x minus 3, 2x minus 1, x plus 2. And you'll notice that the roots of each of those, being 3, 1/2, and negative 2, all appear in this list, right? So all 3 of my roots were in this list. In this video, we saw how to use the rational zero theorem to find a short list of roots to guess and check for higher degree polynomials. In the following videos in this lecture series, we're going to take a look at some more tools that we can use. Catch y'all in the next one.